In 6.2, we will be looking at orthogonal vectors. We have defined two vectors that are orthogonal. And now we are going to talk about a set that is orthogonal. We will use the word orthogonal quite often, so we will use the abbreviation orth. S is a subset of Rn. It has k vectors, v1 to vk. We say S is orthogonal if every two vectors of S are orthogonal. We take out arbitrary two vectors from S, vi and vj. They are orthogonal. We say S is orthonormal, abbreviated as orthon, if S is orthogonal and every vector is a unit vector. For example, S is the set of standard vectors E1 to En. Is the set orthogonal? That's indeed true, because every two vectors are orthogonal. Is it orthonormal? Yes, because every standard vector is a unit vector. Another example. S is the set of these three vectors. This is a subset of R3. Is this a set orthogonal? So we verify if these two are orthogonal. And that's indeed true. And these two, are they orthogonal? That's also true. And then we verify if these two are orthogonal. That's also true. So yes, this is orthogonal set. Is it orthonormal? No, it's not, because they are not standard vectors. A question. Suppose we have a set of k vectors, non-zero vectors. And suppose I tell you that every two vectors are linearly independent. So we take out any two vectors from the set, and they are linearly independent. Can we say that S is linearly independent? That's not true, isn't it? Any two vectors are linearly independent does not imply the whole set of vectors is linearly independent. But it's indeed true if we have the additional condition that S is orthogonal. If we know S is orthogonal and every two are linearly independent, then S is linearly independent. Theorem 6.5. S is a set of k vectors, and S is linearly independent if S is orthogonal. So it's as simple as that. To check whether a set is linearly independent, we know we can apply Gaussian elimination and then check the rank and see if they are linearly independent. But now with orthogonal set, it becomes so much easier. If it is orthogonal and the vectors are non-zero, then the set is linearly independent. To examine whether a set is linearly independent or not, we form the linear combination as before and set the vector to 0. If we want to show the vectors are linearly independent, then we need to show that these coefficients C1 to Ck are all equal to 0. Let's try to use the condition that is given to us. Let's try to use a condition that S is orthogonal. So every two vectors are orthogonal. And orthogonality of the vectors means their dot product is equal to 0. So let's try to introduce dot product. How can we do that? let's multiply both sides by V1 transpose. Then we would get the product, right? And the right hand side is still 0. And this expression by theorem 6.1, we know this, if we have a dot product of a one vector and a sum of vector, we can split it into sum of k dot product like this. C1 V1 transpose V1, C2 V1 transpose V2, all the way to CK V1 transpose VK. Well, there are k terms here, right? But we haven't really used our condition. What is the condition that is given to us? All these V vectors are orthogonal. So, although we have k terms here, we don't really need to concern with ourselves with so many terms, right? Because this term, what is it? V1 transpose V2. This is an orthogonal set. Every two vectors are orthogonal, so this is equal to 0. And similarly, all the other terms is equal to 0. And only the first term is non-zero. Why? Because it's the norm square of V1. So we are left with the C1, V1 transpose V1 equal to 0, and that means C1 is equal to 0. How did we get the conclusion that C1 is equal to 0? We multiply both sides by V1 transpose. Now, if we do that for VI transpose, then we can get the conclusion that Ci is equal to 0. So, we're done. So we have defined orthogonal set. Is there any good thing about orthogonal set? Let's look at a orthogonal basis. Let's use orthogonal set for a basis. Suppose we have a set S as of k v1 to vk vectors, and these are non-zero vectors. And suppose S is an orthogonal basis. It's a basis for subspace V of Rn. Not only it is a basis, it's an orthogonal basis. Let's see what happens when we have an orthogonal basis. Well, S is a basis, so any vector in V can be written as a linear combination of the basis vectors. And the linear combination coefficient C1 to CK, if we put them in a vector, this would be the coordinate vector of the U vector with respect to the basis S. How can we obtain the linear combination coefficient? We know we can collect all these basis vectors into one matrix, and this linear combination can be written in a matrix vector product, like so. And we want this to be equal to U. So the coordinate vector is the unique solution of this system of linear equation. So to obtain the coordinate vector, we need to solve system of linear equation. So we can apply Gaussian elimination, and then we can solve the system of linear equation. This is for the case of a general basis. A general basis that we have for V. But now we have a special basis. Our basis is orthogonal. Does it make any difference here? To use the condition that this is orthogonal basis, so let's try to conjure up with some dot product again. U is equal to this linear combination. So let's try to multiply both sides again by V1 transpose and V1 transpose. Does this look like something that we have done before in the proof of the theorem? Now we have k terms on the right hand side, v1 transpose, and the sum of k vectors, linear combination of k vectors. We can rewrite it as the sum of k dot products. And the sum of these dot products will go away, right? Because this is, after all, a orthogonal set. So this will go away, and all the other terms will go away, except for the first term. By moving the norm square of E1 to the other side, then we get C1. And how can we obtain C1? We can simply take the dot product of U and V1 undivided by the norm square of V1. Then we get C1. It's as simple as that. Similarly, to obtain CI, we can multiply both sides by VI here. Then we get CI. And it's the dot product of U and VI divided by the norm square of VI. So we only need to do dot product and divided it by the norm square. Then we get all the linear combination coefficient. There is no need of applying Gaussian elimination. In this case, these CI coefficients is much easier to compute when S is orthogonal. In many applications of linear algebra, the basis that we use is an orthogonal basis because it's much easier to understand, and it's much easier to use as well.